Hello students, welcome to the next lecture number 40. In this session, we will be discussing the operation of single phase half bridge voltage source inverter with RL load. So observe the terminologies here. We have already discussed half bridge inverter. Uh, So here, voltage source inverter, as you know, the name signifies that the input is a constant DC supply, right? It is a voltage source, right? So whenever input is a constant voltage source, then the inverter is called as voltage source inverter. If the input is uh, the input to the inverter is current, then the type of inverter is called current source inverter, wherein uh, the current will be again converted back to voltage and then will be used for the inverter. Okay, so in the previous session we have already discussed the single phase half bridge inverter with resistive load. Here today we'll be discussing with RL load. Okay, so this was the circuit diagram which you are familiar, wherein this is a bridge network, as you know, and it uses a three terminal input. The input is a three terminal DC supply, as you can see here. So the input Vs is divided, or the circuit is designed in such a way that it is half of the input is taken by considered or used by the upper part of the bridge network, and the second half is used by the lower half of the bridge network, right? So the operation is same here in single phase half bridge, wherein only if the load is RL, if the load is inductive, then how would be the operation differs is what we'll be discussing today. So just to remind you things, this was the output or the waveforms what we had observed for single phase half bridge inverter with resistive load. So observe here, this was the output, the load voltage what you got, a square wave. So if the input was EDC, right? So at the output, you will be getting plus EDC by 2 or minus EDC by 2 based on the conduction of the semiconductor device or the switches what you are using. So if the switch, say for example S1, or you can take it as T1 also, if it is turned on for duration 0 to T by 2, then the output what you will be getting will be plus EDC by 2, right? And between the time duration T by 2 to T, if the second switch, that is, you can also call it as T2, if your next thyristor T2 is conducting, then the output will be minus EDC by 2. And I hope you can recall the working of the bridge network as discussed in the previous session. So observe here the load current will be in phase with the voltage, load voltage, right? Or the output voltage. It is in phase. But if the load is inductive, then there will be slight variation. Let us observe what happens. All right. So if our circuit is something like this, if we have RL load, the load is inductive type, then when T1 is conducting, okay, as you know, the current will be flowing in this direction. So the the current in the circuit will be in this direction, and the load will be storing the energy, right? So if T2 is conducting, then the current in the circuit will be in this direction. So because of that, we know that at the load you will be getting when T1 is conducting, the output will be plus Vs by 2, whether it is Vs or EDC, depending on however you can name it. Yeah, it is input DC. So when T1 is conducting, output will be plus Vs by 2. When T2 is conducting, output voltage will be minus Vs by 2. You know, because of this bridge network. Now, as we had discussed earlier, the role of D1 and D2 will come into picture when the load is inductive. Okay, so based on that, this half bridge inverter can be understood by four distinct modes. Okay, so we will divide the operation of the RL load or this circuit for time duration from 0 to T1 to T1, T2, T3, T4. Okay, so let me just show you the waveform of the circuit here. Yeah, so we will be observing the output of RL load or the half bridge inverter with RL load for different duration of time between 0, T1, T2, T3 and T4. Okay, so based on this, the operation of the bridge can be divided into four distinct modes. Okay, so consider in mode 1, wherein the time is between T1 and T2. Okay, where between T1 and T2, assume that the T1, the thyristor T1 or the switch T1 is turned on. Okay, so as we know, when T1 is turned on, the load voltage will be plus Vs by 2. Okay, and the load current gradually increases, right? And it reaches maximum value at instant T2. Okay, now since the output voltage is plus Vs by 2 and the current is also gradually increasing, okay, that is the polarity of current is also positive. Now the energy is stored in the load, okay, because the load is inductive. Now, when the current reaches maximum value, that is the time when T1 will be turned off. Okay. So when T1 is turned off, um, this is how the current in the circuit or the circuit would be looking. Okay. Say, assume that T1 is turned on. It is acting as a switch and uh, the current in the circuit will be in this direction. So energy is getting stored, and if you observe the output at the load, it is V naught, output is equal to plus Vs by 2. All right. Now between T2 and T3 time duration, that is at time T2, okay, when the current has reached maximum at this point and T2 you are turning off. Okay, so what happens, the the energy stored in the inductor, now it will be reversing and it has to dissipate its energy, right? So because of that, the D2 in the circuit will be getting forward bias, because let us go to the main circuit there. Yes, so now assume that T1 is turned off. So now the energy that is stored is getting dissipated. So the current in the circuit will be start flowing in this way. So which is causing D2 to get forward bias. So D2 will be conducting. Okay. Because this is the current that is getting dissipated, so it is the energy is fed back to the load. Okay, assume here, observe here, the energy is get reversed back to the source due to D2 conducting. Okay, that's why the current will be decreasing, current will be reversed. Okay, and D2 is conducting in the mode 2, that is between T2 and T3. I will show that again in the waveforms. Next, between T3 and T4, okay, at instant T3 and T4, now after the current that is stored here, it is already dissipated via D2. After that, now if you turn on T2, the next switch, if you turn on T2, now we know that because when T2 is conducting, the output at the load will be minus Vs by 2, right? And the current flowing in the circuit will be in this direction, okay? So this will produce negative load voltage. As we know, output voltage will be minus Vs by 2 and a negative load current. So because both the load current and the load voltage are in same polarity, again the energy will be stored by the inductor. Okay. So once the current reaches its maximum value, if that at instant T4, now if you turn off T2 at time instant T4, if you turn off T2, now the the energy that is stored will be fed back to the source again, right? So it is returned back to the upper half of the DC source. So this is a circuit. So at T, uh, T4, it is not T5, it is T4. Okay. So the load current will be, will uh, from T4 to T5, the energy that is stored is getting dissipated via D1. D1 will be now, that is diode D1 will be forward biased, and the the energy is dissipated and the current flow will be in this direction, which is like going back, feeding back to the source. Okay. So let us observe the waveforms here. Now this is the waveform. Now between T1 and T2, if your switch T1, that is thyristor 1, is turned on, or is if it is conducting, then output will be plus. Here it is shown EDC. You can take it as EDC or VS. It is only to do with the nomenclature of the input DC supply, DC source. So here it is EDC by 2 plus EDC by 2 between T1 and T2. See, observe here, switch S1, or you can call it as T1 also. So the current is raising, it is gradually raising. Okay. So current is gradually rising between T1 and T2, and the voltage is also plus EDC by 2. So since both the polarities of the load voltage and load current are positive, the energy is stored, right? And between T2 and T3, as I mentioned, when the thyristor T1 is turned off, D2 will be forward biased, right? So when D2 is forward biased, that is, it gets forward biased because of the energy getting dissipated by the load, right? So the current is here decreasing. The current will be decreasing. As you can observe here, the decreasing current, it is because of the diode D2, and energy is returned back here at this instant. Now, from time instant T3 to T4, when the thyristor T2 or the switch, second switch, if it is turned on, we know that when T2 is conducting, the output voltage will be minus EDC by 2, or you can also take it as minus Vs by 2. Both are same, minus EDC by 2. Okay. And the current is again, it is getting stored, right? So the energy is stored by the load, right, between T3 and T4. And once the current reaches maximum value at T4, if you turn off T2, if you turn off thyristor T2, then the energy is now getting dissipated, right? So between T4 and T5, you can consider this slot or 0 to T1, both meaning same there because it is continuous cycle that is taking place. Okay, so when you're turning off T2, the diode D1 will be forward biased because of the energy getting dissipated by the load. So D1 will be forward bias, and this is the current, the gradually decreasing current that is shown, which is nothing but energy returned back. So whenever energy is getting returned back to the source, diode D1 and D2 will be forward biased. So that completes the circuit there. And whenever thyristor T1 and T2 are forward biased, the load or the energy will be stored by the inductor, right? So because of the inductive load, as you can observe from the waveform here, current will be in this fashion. It will be gradually increasing and decreasing. Okay, so the waveform of the load current is triangular in nature, as you can observe here, and the load voltage will be square wave, as you can note here. Okay, I hope it is clear. The waveform is shown here. So the second line indicates the current due to switch S1 or the thyristor T1. The second line indicates the current due to switch S2 or T2, thyristor T2. This line indicates the current due to diode D1. Okay, and this line indicates the current due to diode D2. Okay, and as you can observe here, between T1 and T2, S1 is on. Between T2 to T3 time duration, diode D2 is conducting or forward bias, or it is on. And T3 to T4, second switch is on. And continuing here, we have it is shown here between 0 to T1 or T4 to T5, it is same, right? So this is the time when diode D1 will be conducting. Okay, so that is the operation of this single phase half bridge voltage source inverter with RL load. Okay, so coming to the circuit equations, so the equation is almost similar to the R load. Only difference is the impedance part, right? Because the load is inductive, there is a L component included there. So the impedance will be just varying. So the instantaneous current I naught, it is given by we have this relation I naught similar to the from the R load of half bridge inverter. But observe here, the only difference is in the denominator you have Zn. Zn is the impedance of the load to the nth component, harmonic component. And we know that the peak amplitude of nth harmonic voltage is given by 2 EDC by n pi. And phi n here, it is nothing but tan inverse of n omega L by R because of the load, RL load, right? The fundamental output power, it is given by P1 RMS, which is equal to E1 RMS into I1 RMS, where E stands for your voltage, into cos theta 1, because it is a fundamental power. Or instead of this, we can also take it as I1 RMS square into R, where E1 RMS is the RMS value of the fundamental output voltage, and I1 RMS is the RMS value of fundamental output current. Okay, and theta 1 is nothing but tan inverse of omega L by R. We know that because n is equal to 1 here. But we know that I1 RMS, we have already familiar from the previous discussion. It is given by 2 EDC by root 2 into pi into this z component, that is square root of R square plus omega L square, right? So P1 RMS, that is fundamental output power, can be written as I1 RMS square into R, where I1, substituting I1 here. So 2 EDC by pi into root 2 root of r square plus omega L square whole square into r. So that will come to 4 EDC square r by 2 pi square r square plus omega square L square. And finally, simplifying, you have the fundamental output power given as 2 EDC square into r by pi square r square plus omega square L square. So instead of EDC, if at all your input DC is Vs, then this parameter will be Vs square. That's the only difference. So I hope it is understood. The operation of single phase half bridge voltage source inverter with RL load. Go through. If you have any clarifications, you can get back to me. See you in the next session.